We're going to go over scalar multiples of vectors. So we're going to talk about this vector here. This vector x, we're not going to actually write what the magnitude of it or a specific bearing direction. We're just going to look at it and we're going to talk about how to apply a scalar multiple to it. So let's say they would like us to draw the scalar multiple of 2 vector x. So in other words, the idea is we're multiplying the magnitude of x by 2. The direction stays the exact same. So in that case, it's the same as writing, or drawing, I should say, a vector roughly like this. And I'm going to recreate one that's going to look like that. I'm just going to pull this farther. That's essentially the idea. Okay. So if you notice, I've just doubled up. This is vector x and vector x. And together they make 2 vector x. The direction is supposed to be roughly the same. I know it's not identical there, but it's supposed to be actually identical. Let's say roughly. Okay, so that would be 2x. We're multiplying its magnitude, so its length. We're assuming that the drawing of the length is a reference to magnitude. If I were to call this a unit vector usually is known to have something as a magnitude of 1. A unit of anything is when we're referring to a value of 1. So in other words, this would be, a magnitude of 1. What? It's unknown. Okay. So in other words, the magnitude of our new vector, because it is of scalar of 2, would be just a magnitude of the value of 2. Direction still being identical to vector x. Okay. Let's say they ask us, well, we would like a half of vector x. Well, we're taking that same vector x, and I'm going to do my best to do a half here. And we're going to take it to about half. Oh man, this is going to be hard. That look like half? The idea is here, this is a half of vector x. So the magnitude of it is a half of what it was before. So because the magnitude used to be 1, the new magnitude of this is just a value of a half. Okay? Direction still identical to the original vector. Let's say they then asked us for negative x, and we've talked about this before. The magnitude of this vector, I'm going to take this one again, will be the exact same. The only difference, I'm going to try this now. I don't know if it'll turn out perfectly. Actually, if I put it beside it, it should work out pretty good. Its direction, yeah, that's good, is the opposite of what it was before. So before, its direction was heading in what seems like a northeast direction. This is now heading in what looks like a southwest direction. The direction of it has changed. The magnitude is the same because technically this negative, you could call it a negative 1. And when we multiply by a value of 1, we're not changing the magnitude of this vector. Its magnitude stays the same. Direction has become the opposite, a reciprocal of it before. So with that same idea at hand, let's say we had the scalar of negative 3. Well, that would be the same idea, and I'm going to use this now as our basis, okay, of taking this vector and adding it to itself 3 times. So which creates a new vector. Try to draw it all out in one shot here. Something like that. Okay. So our negative 3 of vector x, the magnitude of it will still be a value of 3. We don't include negative values in our magnitude. Okay, so the magnitude of this vector is still 3, just like the magnitude of this vector is 1. The negative is letting us know that the direction of the vector has changed. That's the only difference in this. So the idea is we can multiply all vectors by a scalar amount. Okay. So with that being said, let's jump to a new page here. Let's say we were given a question about 2 unit vectors. Unit vector x and unit vector y, let's call it. Okay. We'll say that they look roughly like this. Here is our x, and maybe here is our y. Oops, that's not what I want to do. So here's our unit vectors. We don't know what the actual values of them, but this is 1 unit of x, and this is 1 unit of y. Okay? So we're always going to refer to them kind of as a value of 1 each if we're calling them unit vectors. We'll assume it's still a 1 and a 1 because they're a unit. Okay, very important. Let's say they've even given us a question. They ask us to take the resultant vector of maybe 2y minus x. Okay? They want us to draw out the resultant vector of this effect. Well, in this case, what we're going to be doing, put them on in for the cloner. I know it becomes much easier for me to recreate these things. Is we're going to take these 2y, so we're going to have 2 values of our y. Okay? So that is actually the value of 2y here. We've multiplied by a scalar of 2. We've doubled it, you could say. And our unit vector x, well, we know it's just going to be the direction. So instead of me trying to flip it perfectly, I'm just going to draw an arrow on the other side. Now, normally if we're adding, I'd put this as the tail and that as the tip. But because we're doing the negative of x, I need it to go the other direction. So in other words, things have changed. This now becomes the tail and this becomes the tip, which means now we can change it, group those together. When we add it, this tail needs to go to this end here. Okay? So our resultant vector is now the start to the end here. So this would be our resultant vector. So in other words, if I had to find the magnitude of this such event, the magnitude of this would be just represented as this vector here, 2y minus x. Okay? So that would be a visual representation of the magnitude of 2y minus vector x. Okay? Let's say we actually wanted to find the values of them. Because these are unit vectors, their magnitudes are 1, which means this is a magnitude of 2, this is a magnitude of 1, and this is something we have to figure out. Now, we are missing a piece of information. I do need to know the angle they form. So let's say that the angle between the two, so angle between vector x and vector y, we'll just say it's 60 degrees. Okay? So the angle between the two vectors is 60 degrees. So in other words, if I take in the original and put it here, this would be 60 degrees. How can I apply this information to my triangle in here, to my internal angles in this triangle? Can 60 help us at all? Can I apply it anywhere?
Isn't that one 60?
Which one?
Right there, yeah.
To the far right? Yes. How did you know that that one would be 60? What's that? Guess and check? Yeah, you're right. You got your Z pattern to it, right? I think they go over that. That's the idea here. I think it's called alternating angles is the real name of it. But you're right. You have a Z pattern here because this and this are the same vectors, though they have different directions. This is a negative value. We know it's called collinear. Sorry, collinear is if they're going in the same direction. We know they're parallel. They're not actually collinear. Collinear would be our same direction here. So, because this is 60, we know that this is a value of 60 also. So because that is 60, our one side of our triangle has a magnitude of 2, the other one 1. We can now find the magnitude of our resultant vector using our cosine law from before. So assuming you're very familiar with our cosine law, I'm going to actually write them out as vectors. It's easiest if you guys remember it as A, B, and C. That's fine. I'll show you what it would look like. This formula would look something like this. 2y minus x squared. In other words, this is representing our C, right? This would be our side C. C squared is equal to what's usually known as A squared. Well, in this case, we're just going to call A our 2y. Okay, so 2y. It's the magnitude of 2y is what we're looking for, squared, plus the magnitude of vector x, which is usually known as our plus b squared, okay, minus 2 times scalar 2y times scalar x cos, and now we refer to it as this angle here, the angle of this. We're just going to call it, in this case, our C. We've named it C in this case. And really, that's the same idea of the formula 2 times A times B and cos C. We'll replace c with 60 because we knew it was 60. Okay, here's our 60. It's known as our cos c. A lot of times in your book, they'll write things out as magnitudes of vector. They are relating it to the cosine law. Okay. Now we can replace this because we know the magnitude of 2y is just a value of 2 because it was a unit vector, just like the magnitude of x is just a value of 1. So this part here, we can leave the same as our 2y minus x squared, magnitude of it, is equal to 2 squared plus 1 squared minus 2 times 1 cos 60. Anyone know what cos 60 is? I think you're right. 1 minus 4. Is it 0.5? We'll double check. I'm pretty sure you're right. 60. Smartest guy in the class right there. Times 0.5. All right. Keep this going. This becomes 5 minus 2. Do you guys see what I did there? I combined these two and had these two together because of bed mass. Okay. Which is essentially the idea of 3. Now 3 is equal to, the magnitude of vector 2y minus vector x squared is equal to 3. In other words, the magnitude of 2y, and this is how they represent that magnitude, is equal to root of 3. Okay, so that's what this value would be here, root 3, which is really one of our special looking triangles here, right? And let's get double page. So that's our idea with scalars of a vector. One last thing I do want to talk about is, since we just realized this is one of our special triangles, right? Do a rough draw of it here. This would be 90. This is our 60. This was root 3, 1 and 2, right? Which means this is now 30. Oh, that's not how you draw 30. This is now 30 degrees. Okay? If you're unfamiliar with it, go through BEDMAS to figure all that stuff out. Our resultant vector, we can now say our resultant vector is at an angle. Okay, so it's at an angle of 30 degrees. Scroll up a little, because this angle here is now 30 degrees. It's 30 degrees clockwise of vector y. That would give it some type of bearing. Okay, so 30 degrees clockwise of vector y. That's what I want to add to it. So if we needed to give it a direction, we would just refer to it as one of the other two. You could also say it was 30 degrees, or you could say it was what, 90? 90 degrees clockwise of vector x, right? You could also write it as that way. So either way is acceptable.